Hello my dear friends, myself Ashok Bagda from Dr. Subhash Technical Campus, and in today's lecture we are going to derive an equation of natural frequency for a simple pendulum. Okay, let us start. So this is our we are going to determine an equation of natural frequency for a simple pendulum. So here a simple pendulum is given. So my dear friends, some m mass is attached at a string. The string is pivoted at the fixed point. Now if we displace the string, if mass in this way, then our pendulum is oscillating this way. So here let us consider a simple pendulum having mass m and length l is shown in figure. Now here the string, we consider the string having no mass, we consider massless string, and m, the bob having m as a mass. We can calculate the natural frequency by using following two methods. First one is the energy method and second one is the equilibrium method. Okay, so in this lecture we derive an equation by using these two methods, energy method and also by equilibrium method. Now my dear friends, we know that mass moment of inertia of simple pendulum IO. So this is the center of rotation, center of oscillation of simple pendulum O. So we can say that mass moment of inertia about xx. So IO is equal to ml square. This is a simple equation of mass moment of inertia of simple pendulum. Now as shown in figure, this is the neutral axis. If we displace this pendulum by excitation force, external excitation force, then it will oscillate in this way. But in this case we consider here there is no pivot friction and there is no air resistance. So we neglect two things. One is a pivot friction and second one is a air resistance. So my dear friends, this is initial condition and this is extreme right position of pendulum. So when our bobs reach at extreme right position, then there is a increment in height is small h. So from figure we can say that the small h we use here in this method, we use energy method. So small h is L, this is total height is L minus this one is L cos theta, because this angle is theta. So theta is very small. Okay. So this is L minus L cos theta. So we obtain L in bracket 1 minus cos theta. So we know that the equation of kinetic energy. So simple kinetic energy is equal to 1/2 mv square. So m is mass and v is velocity. But here we consider a rotational kinetic energy because our pendulum is oscillating in this way. So rotational kinetic energy of mass is equal to 1/2 mass moment of inertia IO into theta dot square. So theta dot is the angular velocity. So this is a simple equation of kinetic energy, 1/2 IO into theta dot square. Similarly potential energy. So we know simple equation of potential energy, it is mgh, and in our case h is this is h. In our case h is equal to L in bracket 1 minus cos theta. So mg in bracket L minus L cos theta. So we obtain mgl in bracket 1 minus cos theta. Now according to the law of conservation of energy, total energy remain constant. So total energy is equal to constant. So we can say that total energy here is equal to kinetic energy plus potential energy. So if we take a differentiation of this total energy, then we obtain 0 here. So d by dt in bracket kinetic energy plus potential energy is equal to 0. Now we put the equation. So d by dt here, kinetic energy is equal to 1/2 IO into theta dot square plus potential energy is equal to mgl into bracket 1 minus cos theta bracket complete and whole bracket complete is equal to 0. So if we differentiate, the 1 by 2 is constant, so 1 by 2 IO is also constant. Theta dot square, the differentiation of theta dot square is equal to 2 theta dot into theta double dot plus mgl is constant, the differentiation of 1 is 0 plus equation differentiation of minus cos theta. So cos theta is equal to minus sin theta, so minus minus plus here, sir. Minus minus plus, so sin theta into differentiation of theta is theta dot. So here we take a common, theta dot is common in these two equation. Again, if we simplify this equation, then we obtain IO theta double dot plus MGL sin theta is equal to 0. Now here theta is very small, so we can replace sin theta is equal to theta. So IO theta double dot plus MGL into theta. So we again rearrange this equation, theta double dot is equal to MGL upon IO into theta dot into theta is equal to 0. This is equation number 2. Now comparing equation 1 with theta double dot plus omega n square into theta. So this is the equation of simple harmonic motion. So we obtain omega n square is equal to mgl upon IO. Now we put the value of IO, it is a mass moment of inertia, it is ml square. So here ll cancel, so we finally obtain omega square is equal to g by l. So omega is equal to under root g by l. So frequency fn is equal to, so this is the equation of frequency omega upon 2 pi. So we obtain 1 upon 2 pi under root g by l in a hertz. And if we want to determine time period, then time period is equal to 2 pi upon omega. So 2 pi upon omega, so 2 pi under root g by l. So this is the equation of time period and natural frequency of simple pendulum by energy method. Now we see another method, it is the equilibrium method. Now D'Alembert principle, according to the D'Alembert principle, we know that the total forces acting on the system, the summation of total forces acting on the system should be 0, then our system may be in equilibrium. So we know that in our case there are two types of forces acting on a pendulum. So inertia torque and resisting torque. So this is a resisting torque and this is a torque because of mg. So by using this equation, summation of inertia torque plus external torque is equal to 0. Now we know that inertia torque is nothing but I into theta double dot. Inertia torque is IO into theta double dot. And external torque, here we can say that mg, this component, it is mg sin theta. This component is mg sin theta. So mg sin theta into L, this is a torque. So mg sin theta into L, this is a torque. This is active torque and this is a resisting torque. So again IO into theta double dot plus mg theta into L, because we replace sin theta as a theta because theta is very small. So again we obtain this equation, theta double dot plus mgl upon IO into theta is equal to 0. This is equation. Now again we compare this equation with this simple harmonic equation, theta double dots plus omega n square into theta is equal to 0. So we obtain omega n square is equal to mgl upon IO. So mgl, finally we obtain omega square is equal to g by l. So we obtain omega n is equal to under root g by l. So fn is equal to omega upon 2 pi. So fn is equal to, we obtain 1 upon 2 pi under root g by l in hertz. And similarly, if we want to calculate time period, then time period is equal to 2 pi upon omega. So we obtain 2 pi under root l by g into second. Thank you.
Hello friends, welcome in a lecture of Dynamics of Machinery subject. Myself Mitesh Patel, I am a assistant professor in a mechanical department at a Dr. Subhash Technical Campus, Junagadh. Today's our lecture topic is a natural free vibration of simple pendulum. So in this lecture we discuss or solve the numericals or examples related to natural frequency of simple pendulum, and we find the natural frequency of vibrated pendulum. Okay, So let's start the lecture. First example, it's the find the natural frequency of vibration system, which shown in figure. Means the figure is given, this figure is given, and in this figure the one pendulum is there, the mass is attached to the one rod, and the rod of weight of rod is negligible, only mass is considered of this attached mass, and the two springs are there connected with the pendulum, okay, as shown in figure. The distance of spring from the fulcrum or pivot point of pendulum, the K1 or one spring is the distance A, and K2 stiffness spring, the distance from the fulcrum or pivot point is a B. Okay. Now we have to find out the natural frequency. So we know that the frequency of natural vibration is find out with the help of natural circular frequency upon 2 pi. So we have to find out the natural circular frequency omega n. And how we find out that? The creating or generate the displacement equation of natural frequency or simple harmonic frequency, simple harmonic motion or vibration. Okay, this type of equation we have to create and compare with the simple harmonic displacement equation and find the value of omega n. So this type of equation is we have to create. Here the base should be the same, theta or x. Here the pendulum is the motion in torsional. So the vibration is also called the torsional vibration, not in a linear vibration. So here the equation is generated in form of theta. The base is a theta. So here the equation is generated in the form of theta is equal to 0. This type of equation we have to create. Okay. So let's start. First of all, we displace the mass from mean position to this position, and due to that the force given to the or energy given to the mass is stored into the both spring. One spring is compressed and one spring is in tension, okay, or expand. This energy is stored as a potential energy which are given to the small mass m, okay, and also the potential energy is also stored as a height is increase of the mass. So mgh energy is also increase. So the energy given to the mass is stored into the mgh, and the spring energy force is also considered as a potential energy. So in 3 potential energy store the given energy to the mass, okay. Then we left the mass is moved and the potential energy is converted into the kinetic energy, and when the pendulum reached to the original position or mean position, then the kinetic energy of mass is a maximum, and due to the kinetic energy it's overshoot the original position and move opposite direction to the equilibrium or mean position, okay. So the further pendulum is moved, and from mean position to reach the pendulum to maximum amplitude position, the kinetic energy is converted into the potential energy, and this is stored into the 3 kind of potential energy, and this process is repeat itself in many times and with specific interval of time, and vibration is or oscillation is happens, okay. So now we see that the deflection of spring 1 is defined by deflection or displacement. We can say that the displacement of pendulum is defined by the theta, okay. It's angular displacement, so defined by theta. So displacement of spring is defined by we want to define by theta. So first of all is defined as a x1 deflection of spring or displacement of spring. So x1 is in form of theta. How much is there? the chord length we checked it. So it's a distance is a vertical distance a into angular or angle theta. Okay, so it's a theta. Okay, now spring for or restoring force due to the spring 1. Okay, so the potential energy or spring energy stored into the force. Spring force is a stiffness into displacement. The displacement is how much? X1. So stiffness of spring is a K1 and displacement is a X1, and X1 in form of theta is a K1 A theta. Okay. Now displacement or compression of spring 2 is a X2, and X2 is defined by the B theta. Okay. The X2 is defined by B theta and X1 is defined by A theta, because we have to create equation in form of theta. Okay. So displacement x1 and x2 is converted into the form of theta. Okay. Now spring force or restoring force due to the spring 2, we know that stiffness into displacement. Okay. So stiffness of spring, other spring is a K2 and displacement x2. Now x2 is right in form of theta, so it's a B theta. So K2 B theta is a spring force. Okay. Now inertia, mass moment of inertia of a mass of pendulum about a fulcrum or pivot O. So it's a mass into L square. Okay. So ml square. Okay. Here is a mistake, it is a square. Okay. ml square is a mass moment of inertia of pendulum about a O point. Okay. IO. Now we see the kinetic energy of small mass. Kinetic energy of small mass is a I O omega n square, and omega is defined by theta dot. Okay, theta dot. So omega n square is a theta dot square. So 1/2 I O theta dot square. Okay. Now the potential energy of mass is a mg into L minus L cos theta. How it's happen? How it's find? Check that from the figure. The potential energy due to the height difference is a mgh, and h is defined by this height. Okay, so we have to find out this height. Okay, so first of all we take this triangle and find this distance. Okay, so we find the distance this point to this point with the help of trigonometry. So we'll first consider the triangle, and here the angle is theta. So cos theta is equal to, this length is a L. So we know the, or we find the, we find this distance. Okay, from fulcrum through this. Okay, so this is the unknown. So cos theta is equal to unknown force, and hypotenuse is a L. So this side distance is a L cos theta. Okay, so here the distance is a L cos theta. O2, we can say that OA point. O2A point distance is a L cos theta, and O, this point is known by B. Then OB is a L. So we have to find out the distance AB. So AB is equal to OB minus OA. So OB is a total length L and OA is a L cos theta. Okay. So here distance AB is equal to L minus L cos theta, and AB mg, AB is the potential energy increase or decrease due to the height. Here the potential energy is increased, so it's a positive. If the height is decreased of mass from the equilibrium or mean position, then the potential energy is decreased. Then the potential energy mgh is taken a negative. Here the potential energy mg or h is defined by AB here is, okay, and AB is equal to L minus L cos theta. So here the height difference potential energy is a mg L minus L cos theta, okay, it's mg L minus L cos theta, okay. Now the potential energy of spring, we know that 1 half kx square, okay, for a spring 1 k1 x1 square, or we know that x1 is equal to a theta, or here x1 square is equal to a square theta square, okay. Similarly for a spring energy 2, 1 half k2 x2 square, and x2 is equal to b theta, so x2 square is equal to b square theta square, okay. So here is a potential energy of spring. So we summation of the all potential energy. First, due to the height change, the potential energy mg L minus L cos theta, then the both spring energy, okay, this is the total potential energy. Now according to energy principle or method, it's a total energy of system is equal to constant, okay, total energy of system is constant, okay. Now differentiate the total energy with respect to time, it's a constant, so is a differentiation of total energy is 0, okay. And here total energy is defined by, for a vibration, is a kinetic energy and plus potential energy only, okay. So this is defined by this way, okay, that's here, okay. Now take the all energies in bracket and now differentiate the all things or all elements of this equation. First take this one, or we know that the 1 half IO is the constant, theta dot square differentiation is a 2 theta dot, and theta dot is again differentiation is a theta double dot, okay. So here 2 theta dot, theta double dot. Similarly mg is a constant and the bracket differentiation L is a constant, so is a 0. So here L is a constant, so again is removed, so 0, L is as it is, the differentiation of only d by dt cos theta, okay, and cos theta is a differentiation is a sin theta, and theta is again differentiation is a theta dot, so L sin theta theta dot, okay, of the bracket differentiation, so L sin theta theta dot and mg as it is, so mg L sin theta theta dot, okay. And here 1 half k1 a square is a constant, so differentiation is only theta square differentiation is a 2 theta, and again the theta's differentiation is a theta dot, 2 theta theta dot, okay, and constant is as it is 1 half k1 a square. Similarly for a k2 b square 2 theta theta dot, okay. Now 1 half is take a common and move to the 0 side, okay, and similarly for a theta dot take a theta dot as a constant and transfer to the 0 side, so here value is also 0, and 1 half and theta dot is goes from this equation, so the remaining is a I0 theta double dot, okay. Here 1 half is not need to move to this side, it's already cancelled by 2 in all three terms, okay, only theta dot is take a common and move to the 0 side, okay. So I0 theta double dot, here theta dot is gone, so mgl sin theta, okay, and here 1 half is gone, 2 is cancelled, so k1 a square theta, okay, k1 a square theta, and here k2 b square theta, and theta is taken from common from them both, and here mg sin theta is there, but the right is a mgl theta, because the oscillation or vibration is considered, then vibration amplitude is always very small or small, so if theta is small, then sine theta, if theta is small, then sine theta is tends to theta. Okay, so we can take the sine theta is equal to theta. So here sine theta is mentioned by only theta. Okay, now we know that take the theta common from this both element, and theta is common, then k1a square k2 b square plus mgl. Okay, here is a theta. Okay, now io is divide by both side of the equation. Here io is there, so io is divide, so only theta double dot is there, and here in this equation io is not there, so io is as it is in upon, and here 0 upon I0 is a 0. Okay, so it's a 0, so only in this element the I0 in upon. Okay, now here is a theta, it's a mistake, book typing mistake. Okay, so this equation is equal to the simple harmonic equation of displacement theta double dot omega n square is equal to theta double dot plus omega n square theta is equal to 0. So this equation is similar, and here the bracket value is compared with the omega n square as mentioned. Okay, and now square is removed from the left side, so right side value is in under root. Okay, now with the value of io mass moment of inertia for a pendulum, it's a ml square. So now we know that the equation of frequency Fn is equal to omega n upon 2 pi, and omega n's value or equation of omega n put in this equation, and this is the final equation of natural frequency of given pendulum system. And from this value, put the value of this, all these, then we can find the frequency of given system. Okay, the example is solved. Okay, now the another pendulum, it's in horizontal condition and it's connected with the spring as shown in figure. The figure is given, and in this example mention that to determine the natural frequency of vibration of a system shown in figure. Again, we have to find out the natural frequency of pendulum, but pendulum is in horizontal condition. The length of pendulum capital L, and the distance of spring from the fulcrum is a. Okay, small a. Now if we consider that due to the mass the spring is deflected as a delta. Okay, let's consider that if mass is not there, the rod is connected with the spring in perfect horizontal condition. Okay, if we mass acted to the rod, so due to the weight of mass, rod is slightly angularly displaced or deflection is there of spring. So the displacement of is called the delta. Here is the mention delta. Okay, this is the deflection of spring due to the weight attached to the rod. Okay, and now from this position, if there is displace the mass to some distance, displace to x. Okay, or angular displacement, we can say that the displace the equal to theta to the downward direction as shown in figure. Then release the mass. The given energy of displacement is stored into the potential energy of two types. One is the spring energy and another is the mgh energy. And the potential energy is when they release the mass, the potential energy convert into the kinetic energy and move the pendulum in equilibrium or mean position. And when it's reached to the mean position, the kinetic energy is maximum. So it's overshoot the equilibrium position and move into upward direction. And again the kinetic energy from mean position to maximum displacement position of pendulum, kinetic energy is converted into the potential energy, and now again the potential energy is converted into the kinetic energy, and pendulum is moved to the downward direction. And this procedure or motion or phenomena is repeat itself in specific interval of time, and the oscillation of pendulum or vibration of pendulum is happen. Okay, so now we know that the find the natural frequency, it's a omega n upon 2 pi equation. So we have to find out the omega n circular natural frequency, and how we find that. So creating the equation of theta omega n square, theta is equal to 0, that type of equation we have to develop, and comparing with the equation of omega n square, theta is equal to 0. Here the not omega n square, here the some value is there, and that comparing that two equation we got the value of omega n square. Okay, so we have to develop a theta double dot plus something value, and theta is equal to 0. That type of equation we have to develop from the given system. Okay, with the help of energy method. Okay, so first start the kinetic energy of mass. We know that 1 half I omega square. Okay, and I omega square is defined in form of displacement, means the theta. So it's defined by the angular velocity, means the velocity is a displacement, differentiation with respect to time is a theta dot. Okay, so here I o theta dot square 1 half. Okay, the kinetic energy is a 1 half I o omega square is equal to 1 half I o theta dot square. Okay, now the potential energy of mass is equal to, here the triangle is there. Okay, so here the mass is move up to the downward direction, the height is decreased. So due to the height decreation, the potential energy due to the height is decreased according to h. So mgh is decreased, so mg's energy is in negative form, decreased, so its minus sign is given to the mgh, and we have to find out the h, this h. Okay, this distance h. Okay, and we find out with the help of this triangle. Similarly, earlier the triangle, from triangle we can get that. Okay, and here the what is the phi and theta? Theta is the displacement given to the from the deflection position, and phi is defined by the deflection of pendulum due to the weight is added to the rod. Okay, so some displacement, angular displacement is there and defined by the phi, and phi is a angular deflection due to the weight, and then weight displaced to something distance. Okay, and then release, then vibration is occurs. Okay, so here the sine theta plus phi plus theta is equal to, we have to find outside question mark, and hypotenuse is a L. Okay, so this distance is equal to L sine phi plus theta. Okay, that is mentioned here. Okay, so here the negative sign is there because the energy is decreased. If energy is increased, then the sign is positive, but the energy is decreased due to the height is decreased, so negative sign is given to the mgh. H is a L sine phi plus theta, but the phi is a very small, and it's a deflection, so deflection is a very small, so we can neglect them. So mgl only, theta is considered sine theta. Okay, and negative sign is there. Now the potential energy of spring is defined by the deflection 1 half kx square, and x is the deflection of spring. Okay, sorry, deflection or displacement of spring. So both are considered. So here is the original position of spring. First one is the deflection delta and other one is the displacement. Okay, so x is defined by x plus delta. So here 1 half kx square is equal to 1 half k x, sorry, delta plus x square. Okay, bracket square. Okay, so here the potential energy of spring is a 1 half k in bracket x plus delta square. Okay, now the total kinetic energy is only one there, so it's in, and total potential energy is a spring energy and due to the height energy. Okay, mgh. Now according to energy method, total energy is a constant of system is a constant, and now differentiate with the total energy, so it's a zero differentiation, and total energy is also considered only two energy as a total energy of system in a vibration is a kinetic energy and potential energy. So differentiation of kinetic energy and potential energy is equal to 0. Now put the all values of energies as are mentioned here, kinetic and potential, and now differentiate the all things or all elements. So here we know that 1 half IO differentiation is not done because it's a constant with respect to time. Only theta is changed with respect to time. So theta dot square differentiation is a 2 theta dot, and theta dot again differentiation is a theta double dot. Okay. Now, okay, mgl sin theta, mgl is a constant with respect to time, so is a constant. Only sin theta's differentiation is a minus cos theta. Okay, sorry, sin theta is a cos theta, and again theta's differentiation is a theta. So here sin differentiation is a cot theta, and cos theta's and theta again theta's differentiation is a theta, and negative signs is there. Okay, and here the x and delta is changed. Here the deflection is a constant, it's not changed with time, but the x is there, so delta is the constant, and here the bracket differentiation is there, 1 half k is also constant. So in bracket also only the x differentiation is there. Okay, first in bracket square, so bracket differentiation of bracket should be there, so it's a 2x plus delta, and again the differentiation of this bracket is a only happens of x, it's a delta's differentiation is 0, so x differentiation is a x dot. Okay, so total differentiation of bracket square is a 2x plus delta into multiplication of x dot. Okay, so it's here there, and 1 half k is as it is because it's constant. Okay, now the 2 is cancelled in the both case, and theta dot is take a common, and here theta dot not take a common because here is a x dot, so x dot is defined by the in form of theta. So here x is equal to a theta, so if differentiate with respect to time dx, and here d by dt, so here a is a constant, so theta's differentiation is theta dot, and x differentiation is x dot, and a is as it is. Okay, so x dot is equal to a theta dot. Okay, so here now theta dot is take a common and move to the 0 side, and here not a change, 0 is as it is 0, and theta dot is gone. Okay, here the bracket is first open and then take the theta dots common. Okay, bracket is open, so k and a theta dot is multiply with both element. Okay. Now the remaining elements are there when theta dose is gone from the all element. Now here K delta I is equal to mgl. How it's equal? It's a torque in equal. We know that in earlier, if the rod is there, only rod is there, not weight is there, the spring in equilibrium condition. But when the weight is connected to the rod, the spring is slightly deflect from its position to the delta. Okay. Now at that position, spring and mass are both in equilibrium condition and the pendulum is steady, not move. Okay. So it's in equilibrium condition. So that both torque are equal. Which torque? The torque generated due to the spring force and torque generated due to the gravitational force or weight of mass. Weight of this attached device or attached weight. Okay. So two torque is there. Spring force torque. Spring force is a K and deflection is the delta, K delta of the spring force, and for a torque is a force perpendicular distance. So perpendicular distance is a, so spring force is a K delta A. Sorry, spring torque is a K delta A. And now the gravitational torque is there, is a gravitational weight mg, okay, and distance is a L. So K delta A is equal to mgl. Okay. So here K delta A is equal to mgl. We can put that. So here if mgl is taken, so mgl is cancelled because it's plus and it's negative. So its differentiation 0. So only two elements are there. And right here I theta double dot and K square. And now I0 is divided by both side, left side and right side. So IO divided by this element, so IO cancel, so only theta double dot is there. And here the K a square theta is divided by IO, but the IO is not there, so it's in upon, and here 0 upon IO, it's a 0. Okay. Now this equation is equal to the omega n square simple harmonic motions displacement equation, and this comparing these two equations we get the omega n value in bracket. Okay. So omega n square is equal to K square upon IO, and IO's value is put is a ml square. For a pendulum, mass moment of inertia of pendulum is a ml square, and m is the mass attached or weight attached at end. Okay. So it's a ml square. Okay. Mass moment of inertia of pendulum. Now for the natural frequency Fn is equal to omega n upon 2 pi, and omega n is equal to this equation is there, so you put the value, and this is the final equation of natural frequency of a given system. And if you put the value of stiffness, mass and length L, pendulum length L, then we can find out the natural frequency of pendulum. Okay. So thank you all friends. Okay. I hope you very well understand how the natural frequency of pendulum numericals or examples of pendulum it's solved. So you can easily solve the natural frequencies example with the help of energy method. We also seen in the another lecture. In this lecture we solve the example of spring and mass system, and in this lecture we solve the example of pendulum of natural frequency with the help of energy method. Okay. I hope you very understand all things. Okay. Thank you for listening or watching my video lecture. Okay. Thank you.